static you mistake for silence. Right now, about 100 trillion of something are going through your chest, and none of them will ever touch you. Not once. Not tonight. Not in your whole life. No matter how still you hold yourself. You're lying there, maybe, or sitting with the lights already half off, and there's a heaviness behind the eyes that says the day is basically done. And somewhere in that stillness, without asking, without so much as a knock, they're already passing through the blanket, through the mattress, through you and the floor under you, and the concrete under that, like the whole house is made of something slightly less solid than it pretends to be. This is Sleepy Science Channel, if that name means anything to you yet, and it's fine if it doesn't. I only found this one myself a few nights ago, reading late, and I haven't been able to put it down since. The way you can't put down a sound you keep almost hearing. The particles are called neutrinos. Say it once and let it go. You won't need the name again for a while. What matters isn't the label. What matters is where they come from, which is mostly the sun, pouring out of its core by the trillion second by second in every direction at once, and where they're going, which is everywhere, forever, through anything that gets in the way. Steel doesn't stop them. Lead doesn't stop them. A neutrino could pass through a wall of solid lead, a light year thick, and more likely than not, come out the other side exactly as it went in, unbothered, unchanged, in a hurry to be somewhere else. There isn't a somewhere else, really. There's just more universe, and they're headed into all of it. Here's the part that sits strangely once you let it. You have never felt one. Not a flicker. Not the smallest pressure. Something is happening to your body continuously, at a rate too fast to count, and your nervous system, which will alert you to a hair on your arm, has absolutely nothing to say about it. It isn't built to notice. It was never going to be built to notice. The gap between what happens to you and what you're capable of feeling is so much wider than most people walk around assuming. If you've ever wondered why the room feels quiet even when it technically isn't, that's some of what I mean. It isn't silence. It's just silence to you. Consider what it actually took for one of these to reach you tonight. Deep in the sun's core, at a pressure that would flatten anything built on Earth to something thinner than paper, 2 protons are forced together against their own resistance. Every particle in that furnace repelling every other, the way like charges always repel, until sheer crowding and heat and gravity's endless downward insistence win out anyway. Now and then, a proton becomes a neutron. It has to for fusion to work at all, and in that instant of becoming, something has to carry away a sliver of charge and a scrap of spin that don't belong anywhere else. That something is a neutrino. It is born already leaving. It does not pause to be part of the star it came from. Photons, by contrast, are famously patient. A photon produced at the sun's core can spend tens of thousands of years bouncing from particle to particle before it fights its way out to the surface and finally escapes as sunlight, which is part of why the light warming your face on any given afternoon started its journey when a different set of ancestors was cooking in a different set of fires. The neutrino has no such patience and needs none. It barely notices the material it's supposedly trapped inside. It leaves the sun's core and reaches the sun's surface in about 2 seconds, then crosses 93 million miles of open space in a little over 8 minutes, and then, if you happen to be facing the wrong way at the wrong moment, it goes through your skull without slowing down even slightly, and continues on into the ground, and through the mantle, and out the other side of the planet and back into space, having spent in total a little less than a heartbeat's worth of attention on the entire Earth. That is the ordinary case. The overwhelming majority of solar neutrinos that reach you pass through the full body of the planet as if it simply weren't there, which is a strange thing to know while lying on top of that same planet, trusting it to hold you. The particles are called neutrinos. Say it once and let it go. You won't need the name again for a while. What matters isn't the label. What matters is where they come from, which is mostly the sun, pouring out of its core by the trillion second by second in every direction at once, and where they're going, which is everywhere, forever, through anything that gets in the way. There's an old story about how this particle came to be believed in before it was ever caught, and it's worth telling slowly because it explains something about how strange this whole subject has always been, even to the people closest to it. In the winter of 1930, a physicist named Wolfgang Pauli was looking at a problem that shouldn't have existed. When certain unstable atoms decayed, a process called beta decay, the energy coming out the other end was always a little less than the energy that had gone in. Energy isn't supposed to just vanish. It had never vanished before, in any experiment, in any equation anyone trusted. So either the most reliable law in physics was quietly failing inside every radioactive atom on Earth, or something was slipping out uncounted, carrying the missing energy away before anyone could measure it. Pauli didn't like either option. He wrote a letter to a group of colleagues gathered at a conference he couldn't attend, opening it with an apology, calling his own idea a desperate remedy, proposing an invisible, weightless, chargeless particle that would explain the missing energy, but that might, he admitted, never be detectable at all. He didn't publish it as a triumph. He treated it almost as a confession, the kind of idea you offer only because every other explanation has already failed you. It would be 26 years before anyone caught one. The catching itself is its own kind of strange patience. In 1956, two American physicists, Clyde Cowan and Frederick Reines, built a detector next to a nuclear reactor in South Carolina. Reactors being, among other things, extraordinarily generous producers of neutrinos, the byproducts of all that decaying fuel inside. And they waited for the occasional neutrino to do the one thing in 10 trillion it might actually do: strike a proton in their tank of water and cadmium chloride and produce a fleeting characteristic flash of light. Most nights, nothing. Some nights, a flicker that could have been anything. They sent Pauli a telegram once they were sure. He was 66, near the end of his life, and by all accounts genuinely moved to learn that the desperate remedy had turned out to be real, that the particle he had proposed almost apologetically as a placeholder for his own confusion had been sitting there the whole time, streaming through reactors and stars and bedrooms, waiting for someone patient enough to build a trap, sensitive enough to notice it stepping into one. Since then, the traps have gotten larger, not smaller, because the particle never got any easier to catch. Somewhere under a mountain in Japan there's a detector called Super Kamiokande, a tank the size of a 14-story building filled with 50,000 tons of ultra-pure water, lined wall to wall with more than 11,000 light-sensitive tubes, sitting nearly a mile beneath solid rock, specifically so that everything except neutrinos gets filtered out by the mountain above it. Even buried that deep, even built that large, even watching that patiently, the detector catches only a handful of solar neutrinos a day, out of the uncountable trillions that pass through it in that same 24 hours. Somewhere else, in the ice beneath the South Pole, there's an observatory called IceCube, not a tank at all this time, but a full cubic kilometre of ancient glacial ice, threaded with more than 5,000 sensors lowered on cables into holes drilled 1.5 miles down, built to catch the rarer, wilder neutrinos that come not from the sun but from exploding stars and feeding black holes on the far side of the visible universe. The engineering required to notice something that barely interacts with anything is, on its own, one of the stranger monuments humans have built. Cathedrals constructed not to house something, but to occasionally catch it failing to pass through. The way these tanks actually catch a neutrino, on the rare occasion they do, is its own small piece of theatre, even if no one is there to watch it happen. When a neutrino strikes something inside all that ultra-pure water, it produces a charged particle moving faster than light travels through that same water, which sounds impossible only because we're used to comparing everything to light speed in a vacuum, and water slows light down more than it slows a particle freshly launched by a collision. That charged particle, briefly outrunning the local speed limit for light, produces a faint cone of blue light called Cherenkov radiation, the optical equivalent of a sonic boom, a shock wave of glow spreading outward through the tank in a perfect ring, caught an instant later by whichever of those 11,000 tubes happen to be lined up in its path. The whole event lasts a few billionths of a second. It leaves behind a ring of light precise enough to say where the neutrino came from and roughly how fast it was going, and then it's over, and the tank goes back to being 50,000 tons of very still, very patient water, waiting for the next one, which might arrive in a few minutes or might not arrive for the rest of the day. Physicists have a nickname for the neutrino, half affectionate, half exasperated, the ghost particle. It's not a poetic flourish so much as an honest description of what it's like to work with something that interacts so rarely. To give the rarity some shape, a neutrino passing through a slab of ordinary lead would need that slab to be roughly a light-year thick, thicker than the distance to the nearest star, before it had even a 50-50 chance of actually hitting something inside it and stopping. Everything else humans have ever built to stop a moving object, armor, bunkers, mountains, planets, works by relying on the fact that matter is, at some scale, dense enough to get in the way. Neutrinos expose how much of that density is really just electromagnetic bluff, forces pushing back on forces, none of it actually solid in the way a fist assumes a wall is solid. The neutrino ignores all of that bluffing completely, because it doesn't interact electromagnetically at all. It only ever notices the weak nuclear force and gravity, both of which are, at the scale of a single particle, meeting a single nucleus, almost comically faint. It isn't that the neutrino is small. Plenty of things are small and still get stopped by a wall. It's that the neutrino is, in the truest sense available to physics, uninterested. built out of a kind of matter that simply doesn't participate in the version of solidity your body relies on to keep its shape. A person somewhere left a comment on an earlier upload, guessing that if you counted every neutrino that passed through your body in a lifetime, the number would be bigger than the number of stars in the visible universe. I looked it up out of curiosity more than doubt. They weren't far off. Over roughly 80 years of an ordinary life spent mostly indoors, mostly asleep at the hours that matter least, a person will be passed through by something on the order of 100 quadrillion trillion neutrinos, a number so far past the count of stars that the comparison almost undersells it. I don't know what that does to a person to carry around once they know it, but I'd be curious what it does to you. You don't have to say, but if you want to leave that thought somewhere, I do read them, eventually, usually late, usually like this. There's a kind of trust required to keep making these, not knowing who's actually still listening by this point in a video. And somehow there always are a few of you, which is the only reason there's a next one. So, you're lying there. The neutrinos are going through you at roughly the pace they always do, which is to say constantly, which is to say they were going through you before you started listening, and they'll be going through you after you stop. Nothing about that changes whether you're awake for it. Most of them are moving at very close to the speed of light, which means the sun you're not looking at right now already sent this one. It left roughly 8 minutes ago. It has been 8 minutes since that neutrino was part of a star, and it is here now, in this room, gone before the sentence describing it is finished. Some of them aren't from the sun at all. Some are older than the sun. Some were made in the collapse of a star that finished collapsing before the Earth existed, and they've been crossing the space between then and now this whole time, and one of the last things they'll ever do, the very last thing, arguably, before they vanish back into the rest of the universe, is pass through a bedroom in a house you happen to be lying in tonight. Here's a detail that turns the whole subject inward, if you let it. You are not only something neutrinos pass through, you are, in a small way, something that makes them. Buried in your bones and muscle, in a concentration too small to notice and too old to avoid, is a radioactive form of potassium, potassium-40, left over from the same stellar furnaces that made every other atom in your body and every second inside every human being alive. A small number of those atoms decay, and in decaying some of them emit an antineutrino, a close cousin of the particle that's been the subject of this entire chapter. A typical adult body produces something on the order of 350 million of these every day, quietly, without ceremony, leaving at the speed of light in every direction, headed the same way outward that the sun's neutrinos are headed inward. You're not simply a target for this kind of physics. For your entire life, without doing anything, without trying, you have also been a source of it, a small, warm, decaying furnace of your own, sending a faint stream of ghosts out into the dark alongside every other star and every other body doing exactly the same thing, everywhere, all the time, mostly unnoticed, mostly uncounted, and entirely real regardless. There's no reason it should matter to you. It doesn't change your morning. It won't show up on anything. And still, there's something about being the very last obstacle a 14-billion-year-old particle almost didn't clear, and clearing you cost it nothing, and it doesn't even register that you were there. There's a further detail that only surfaces once you stay with this long enough, and it concerns what these particles are actually made of, or rather what kind they come in, because it turns out there isn't just one flavour of neutrino, there are three. One tied to the electron, one to a heavier cousin called the muon, one to a heavier cousin still called the tau. And for decades, physicists built detectors expecting a certain steady count of the electron kind arriving from the Sun, only to find, again and again, roughly a third as many as the equations predicted. For a while, this looked like a serious problem, the kind of discrepancy that suggests either the Sun's furnace or the detector or the whole theory of how stars burn was quietly wrong somewhere. What turned out to be true instead was stranger than any of those options. The neutrinos aren't disappearing, they're changing. A particle that leaves the Sun's core as one flavour can arrive at Earth as another, oscillating between identities mid-flight, a kind of shape-shifting that shouldn't be possible for something with no mass at all, which is how physicists learned, almost as an aside, that neutrinos do carry a tiny mass after all, vanishingly small, but not quite zero, a detail the original theory hadn't required and hadn't predicted, and had to be dragged toward by the data itself. There's one event worth sitting with a little longer, because it's the closest this subject ever came to drama, and even then the drama happened almost entirely out of sight. In February of 1987, a star in a neighbouring galaxy called the Large Magellanic Cloud finished its life and collapsed, and in the final seconds of that collapse, seconds, not hours, it released more energy in neutrinos alone than the Sun will produce over its entire 10 billion year existence. Almost all of that energy left as neutrinos, not light, because neutrinos escape a collapsing star's core almost immediately, while the light generated by the same event has to fight its way out through the star's own collapsing bulk before it can finally reach open space. The neutrinos from that explosion crossed 168,000 light-years of empty space and arrived at Earth on the 9th of February, and detectors on 3 separate continents, quietly running, watching for exactly nothing in particular, the way they always are, caught a sudden handful of them within a span of about 13 seconds. It wasn't until nearly 3 hours later that the visible light from the same explosion finally reached telescopes and lit up the night sky as a new temporary star bright enough to be seen without a telescope at all, the first supernova visible to the naked eye in nearly 400 years. For 3 hours, a small number of physicists in scattered basements somewhere on Earth knew that a star had died before anyone looking up at the sky did. They didn't know it yet either, not with certainty. The flashes had to be checked, cross-referenced, argued over, but the information had already arrived. It was just quieter than starlight and slower to be believed. There's an older, colder relic than even that, one that never announces itself with any flash at all. In the first fraction of a second after the universe began, when everything was compressed into something almost too dense and too hot to describe honestly, neutrinos decoupled from the rest of matter far earlier than light did. Light wouldn't manage to travel freely for another few 100,000 years, trapped bouncing through a hot fog of charged particles, but neutrinos, barely interacting with anything even then, simply left. They've been drifting ever since, cooling as the universe expanded around them, and by now, theory says, they fill all of space at a density of a few hundred per cubic centimetre everywhere, including the cubic centimetre of air in front of your face right now. Nobody has ever detected this cosmic neutrino background directly. It's far too faint, far too gentle, moving far too slowly by the time it reaches us for any existing instrument to register it. But if the calculations are right, it means there is a second, older kind of afterglow sitting quietly behind the one astronomers already photograph. A picture of the universe taken not hundreds of thousands of years after the beginning, the way the famous one is, but taken in the first second. Nobody has developed the film yet. It's simply sitting there, everywhere, waiting for an instrument patient enough someday to notice it. You go on breathing, mostly unaware. It goes on going. I don't fully understand why this stays with me the way it does. Maybe it's just the scale of it. The sheer, uncountable, wall-to-wall traffic of a universe doing something enormous through a body that has no idea. Maybe it's simpler than that. Maybe it's just strange to be told you're full of holes nobody can see and structure at the same time. Both true, neither cancelling the other out. The room is quiet now. It was quiet a minute ago too. Nothing changed. Something is still moving through it. The weight nobody signed for. Start far enough back and a galaxy looks like it's barely moving. Patient, almost lazy, the way a slow river looks lazy from a bridge when really something enormous is underneath it, doing all the work. I've come back to this one more than once over the years, because it never quite finishes settling. Here's the shape of it. A galaxy spins, and the stars near its edge should be flung off, or at least lag far behind the stars near the centre. That's how spinning things work. That's how a merry-go-round works. Faster near the middle, slower toward the rail. Except galaxies don't do that. The stars way out at the edge move almost as fast as the ones near the core, which should be impossible unless something is holding the whole outer structure together that isn't visible from here, or from anywhere, or possibly from any distance at all, ever, no matter what we build to look. That something has a name. Dark matter. Though the name explains almost nothing about what it is. It only tells you what it does. It holds. It doesn't shine. It doesn't block light the way a planet blocks light, casting a clean little shadow you could measure. It just sits there, distributed in a vast loose halo around and through the galaxy, contributing mass, contributing gravity, contributing nothing else that we've ever managed to detect directly. Picture the amount required, roughly 5 times more of it than all the visible matter combined, more than every star, every planet, every cloud of gas in every galaxy you could point a telescope at, added together and multiplied, and none of it visible, not faintly visible, not visible with a better camera, structurally, permanently unavailable to sight by whatever it's made of. There's an old habit in this field of assuming that if you can't see something, it probably isn't very big. Dark matter breaks that habit completely, and it's been breaking it for almost a century now, since a Swiss astronomer named Fritz Zwicky first noticed galaxies in a cluster moving faster than their visible mass could explain and figured correctly that something was missing from the picture. Zwicky's own story is worth slowing down for because for decades almost nobody believed him. In 1933, studying a cluster of galaxies in the constellation Coma Berenices, thousands of galaxies, all gravitationally bound to one another, all orbiting a shared centre of mass the way planets orbit a sun. He measured how fast the individual galaxies were moving relative to the cluster as a whole, and the number came back absurd. At the speeds he was measuring, the visible mass of the cluster wasn't nearly enough gravity to hold it together. By his calculation, the cluster needed something like 400 times more mass than could be accounted for by counting stars and estimating their glow. Or it should have flown apart entirely, its galaxies scattering into the surrounding dark like sparks off a wheel with no rim. He called the missing material Dunkelmaterie, dark matter in his own German, and largely the field shrugged. Zwicky had a reputation, not always a kind one, for being difficult, blunt, quick to insult colleagues he thought were being sloppy, and a wildly oversized claim from a man like that was easy for a cautious field to set aside as eccentricity rather than evidence. It sat mostly unexamined for nearly 40 years. It was a different kind of measurement decades later that made the problem impossible to ignore. In the 1970s, an American astronomer named Vera Rubin, working with instruments precise enough to track the speed of gas and stars at different distances from a galaxy's center, began charting what are called rotation curves, essentially a plot of how fast material moves as you go from the crowded core of a galaxy out toward its sparse, quiet edges. The prediction, based purely on visible mass, was straightforward. Speed should drop off with distance, the same way a planet farther from the Sun moves more slowly in its orbit than one close in. Rubin's measurements, galaxy after galaxy, refused to drop off. The curves stayed flat, sometimes for as long as the data could reach, stars at the far edge of a galactic disk moving at nearly the same velocity as stars deep inside it. A result so consistent across so many separate galaxies that it stopped looking like measurement error and started looking like a rule. Rubin herself was famously careful in how she described what she'd found, resisting more dramatic language for years, letting the data itself make the case. It made the case eventually. By the late 1970s, what Zwicky had proposed as an eccentric fix for one cluster had become, through Rubin's patient repetition, a pattern too widespread to be a mistake. Picture the amount required again, but now picture where it actually sits, because it's not spread evenly through a galaxy, the way you might picture fog filling a room. The dark matter halo around a typical spiral galaxy extends far past the visible disk of stars, often several times wider than the galaxy you'd actually photograph, an invisible sphere of scaffolding surrounding a comparatively small bright disk like a single lit room in the middle of a much larger unlit house. The visible galaxy, the part with the spiral arms and the bright core and the dust lanes you'd recognize from any photograph, is closer to a decoration sitting inside a much larger structure than it is the structure itself. Nobody's found it. Not directly. Detectors sit in mines a mile underground, shielded from cosmic noise, waiting for one of these particles to bump into something and leave a trace. Mostly they wait. That's most of the job, actually. Waiting in the dark, underground, for a nudge that might not come this year or this decade. The waiting has a name and a method, and both are stranger than you'd expect from something built to look for nothing. Detectors like these, tanks of liquid xenon mostly, cooled to temperatures colder than most of the universe ever gets on its own, buried under mountains or at the bottom of old mines specifically to filter out the ordinary cosmic rays that would otherwise drown out any faint signal, are built on a simple bet that dark matter, whatever it turns out to be, occasionally collides with an ordinary atomic nucleus, hard enough to produce a tiny measurable flash or a tiny measurable recoil. The word occasionally is doing enormous work in that sentence. Some of the most sensitive detectors ever built have run for years, watching continuously, and recorded exactly 0 confirmed events. Not because the experiment failed, but because that's what a genuinely rare interaction looks like from the outside. A negative result, patiently earned over years of underground silence, still narrows down what dark matter can't be, which is its own kind of progress, even if it never once produces the triumphant flash a documentary would want. There are other approaches that don't wait underground at all, that instead try to make the particle themselves. Machines like the Large Hadron Collider smash ordinary particles together at speeds and energies close to what existed a fraction of a second after the universe began, on the chance that a dark matter particle might be created briefly in the wreckage before slipping away entirely undetected, noticed only by its absence, by a small, unaccounted for gap in the energy and momentum on either side of the collision, the way you'd know something had walked through a room only because a candle you'd left burning suddenly flickered. And there's a third approach that looks outward instead of down or sideways, watching for dark matter to occasionally destroy itself. Some theories predict that if 2 dark matter particles collide with each other, in the crowded center of a galaxy where the halo is densest, they might annihilate and produce a telltale burst of ordinary particles, gamma rays especially, that a telescope could, in principle, catch drifting outward from exactly the regions where the invisible scaffolding should be thickest. Decades of looking. No confirmed detection yet, by any of the 3 methods, anywhere. And still, the case for the scaffolding itself has only gotten stronger with time, because rotation curves aren't the only evidence anymore. Before physicists settled on the strange exotic particle explanation that dominates the field now, there was a simpler guess worth mentioning, if only because it shows how carefully this mystery has been tested against the boring answer first. Maybe, the thinking went in the 1980s and 90s, the missing mass wasn't exotic at all. Maybe it was just ordinary matter that happened to be dark, in the plain sense of not producing much light. Burned out stars, failed stars that never ignited, rogue planets and black holes drifting between the visible ones, too faint and too scattered to show up in any telescope. These candidates got a name, MACHOs, short for Massive Compact Halo Objects, chosen partly as a wink at the acronym for the exotic alternative, WIMPs, weakly interacting massive particles. Astronomers went looking for MACHOs the only way you can look for something invisible and compact, by watching for the brief, telltale brightening that happens when one drifts directly in front of a distant star and its gravity briefly acts like a lens, magnifying the star's light for a matter of days before fading back to normal. They found some, not nearly enough. The surveys that watched millions of stars for years waiting for these gravitational flickers turned up far too few events to account for more than a small fraction of the missing mass, which meant the boring answer. Ordinary matter, just dim and out of sight, had been tested directly and had failed the test. Whatever's out there, in other words, isn't simply matter we already understand hiding in the dark. It has to be something categorically different. Matter that doesn't burn out because it was never going to ignite in the first place. Matter with no ordinary future as a star or a planet, because it doesn't interact with light or with itself in any of the ways ordinary matter does. That failure pushed the field harder toward the wimp side of the joke, toward the idea of an entirely new category of particle, one that interacts through gravity and perhaps the weak nuclear force, and essentially nothing else. It's worth saying plainly that this isn't a small ask. It means most of the mass of the universe is made of something that has never been directly observed, something outside the otherwise very successful standard model of particle physics that describes everything else. Quarks, electrons, photons, the whole familiar cast, with extraordinary precision. Adding a new category of matter to explain a gravitational anomaly is the kind of move a field doesn't make lightly, and for a while a determined minority of physicists pushed back against making it at all, arguing that the anomaly might instead mean gravity. Itself behaves differently at galactic scales than Newton or Einstein predicted. A proposal called modified Newtonian dynamics, or MOND, which can reproduce flat rotation curves in individual galaxies without requiring any invisible mass at all, simply by tweaking how gravity weakens with distance once you get far enough from a galaxy's center. MOND has never managed the trick that dark matter manages almost effortlessly: explaining the bullet cluster, explaining the large-scale structure of the universe, explaining the exact pattern of the cosmic microwave background. And so it remains a minority position, kept alive mostly because it's a useful reminder that even a century-old mystery this well-supported still deserves the discomfort of a rival explanation, rather than the false comfort of unanimous agreement. There's a particular photograph, taken with two colliding clusters of galaxies nicknamed the bullet cluster, that comes as close as this field gets to a smoking gun. When two galaxy clusters collide, most of the visible ordinary matter, mostly hot gas, which makes up the bulk of a cluster's normal mass, collides and slows down and gets left behind in the middle, glowing brightly in X-rays where astronomers can map it precisely. But when researchers separately mapped where the gravity was actually strongest, using the way that mass bends light from more distant galaxies behind it, the strongest gravity wasn't sitting where the glowing gas had piled up. It had passed straight through, undisturbed, continuing on ahead of the visible wreckage. Exactly what you'd expect if most of each cluster's mass barely interacts with anything at all, including itself, and simply sailed through the collision while the ordinary matter crashed and slowed. It is essentially a photograph of the invisible mass and the visible mass in the same frame, caught in the act of disagreeing about where to be. There's a second kind of evidence, older than any of the particle hunting, that comes not from watching one galaxy, but from mapping how galaxies are arranged relative to each other across the largest scales anyone has ever charted. If you plot the positions of hundreds of thousands of galaxies across a large enough volume of space, you don't get an even scatter, the way you might expect from something that started as a roughly uniform hot soup after the Big Bang. You get structure, long filaments of galaxies strung together like threads, vast empty voids between them large enough to be measured in hundreds of millions of light years across, everything arranged into something astronomers have taken to calling, without much exaggeration, the cosmic web. That structure didn't assemble itself out of visible matter alone. Ordinary matter in the early universe was still tightly coupled to light, bouncing around in a hot fog that resisted clumping together under its own gravity for hundreds of thousands of years. Dark matter wasn't, because it doesn't interact with light at all. It was free to start clumping almost immediately, forming a rough gravitational skeleton throughout the young universe well before ordinary matter was able to join it, falling into the gravity wells that dark matter had already carved out, gathering along the same filaments, lighting up the framework after the fact, the way frost traces the shape of a spider web that was already there in the dark, invisible, until something visible finally settled onto it. Run a simulation of the universe's evolution without dark matter in the mix, using only the gravity of ordinary matter, and you don't get the cosmic web at all. You get something far smoother, far less structured, a universe that never quite manages to build itself into galaxies on the timeline we can actually observe. Add the dark matter back in roughly the proportion the rotation curves already demanded, and the simulated universe suddenly looks like the real one. Filaments, voids, clusters, all falling into place with an accuracy that's hard to write off as coincidence. The way light itself bends around all of this mass, visible and invisible both, offers still another way to weigh what can't be seen directly. Massive objects curve the space around them, and light passing close enough follows that curve, arriving bent, magnified, sometimes split into multiple images of the same distant object, a phenomenon called gravitational lensing that Einstein predicted decades before anyone had the instruments to actually catch it happening. Point a sufficiently sensitive telescope at a massive galaxy cluster, and if you look carefully at the space around it, you'll often find faint smeared arcs of light, the stretched, distorted images of much more distant galaxies, their light bent on its way past the cluster's gravity like a straight line drawn through a lens. Map the exact pattern and strength of that bending, and you can calculate with real precision exactly how much mass is doing the bending, whether or not any of that mass gives off so much as a photon of its own. Every time this measurement has been made, the mass required to produce the observed bending is far larger than the visible mass sitting in plain sight at the cluster's centre. The invisible scaffolding announcing its presence not by shining, but by the way it quietly rearranges the light of galaxies far behind it. Borrowed evidence from a source that has nothing to do with the halo itself. Zoom back out to the galaxy from the start. It's still turning, unbothered, held in place by a scaffold we can only infer from its effects. The way you'd know a large dog was in a dark room by the sound of it breathing, without ever seeing its shape. Some nights I think about how strange it is that the universe's most common form of mass has never once been photographed, never once been held, never once done anything except hold everything else together from a distance too complete to argue with. It doesn't announce itself. It doesn't need to. The galaxy spins whether or not you ever learn its name, whether or not any detector ever catches it mid-collision, whether or not the room you're lying in tonight has any halo of its own passing quietly through it, unbothered, uncounted, entirely indifferent to whether you're awake for it. Room enough for nothing. Make a fist. Feel it close. Feel the knuckles meet knuckles. Feel how solid that is. It isn't really. not the way it feels. Inside every atom that makes up your hand, there's a nucleus. Tiny, dense, almost all the mass. And that there's a huge stretch of essentially nothing before you reach the electrons circling it. If an atom were the size of a football stadium, the nucleus would be a marble at the 50-yard line. Everything else, all that space between marble and stands, is emptiness. Not dusty emptiness, not thin fog. Actual room with almost nothing in it. Sit with the ratio for a moment, because it's easy to say and hard to actually picture. A hydrogen atom is roughly 100,000 times wider than its own nucleus. Scale a human being up by that same ratio, and you'd be looking at something wider than the distance from the Earth to well past the orbit of the Moon, all of it built around a single, dense, central point smaller than a grain of sand. That's not a difference of degree. That's a difference between two ways of being mostly nothing, and a little bit of something, and your entire body, every part of it, is built this way, over and over, atom after atom, all the way down. And it stacks, atom after atom, gap after gap, layered until you have a hand, a fist, a fact you were told as a child, that skin can't pass through skin. It can't, but not because it's solid the way you think solid means. It's electromagnetic repulsion, mostly. Electron clouds pushing against electron clouds, refusing to overlap, holding two fists at a polite distance even when you're trying your hardest to close that distance. Slow down here, because this is the part that's easy to walk past too quickly. The electrons themselves aren't sitting at the edge of that stadium like fans in their seats, waiting politely for a nucleus to notice them. They don't occupy a fixed point at all, not in any sense a fist would recognize as a location. What surrounds the nucleus is closer to a probability, a fuzzy, shifting cloud, describing where an electron is more or less likely to be found if you tried to catch it in the act of being somewhere, which you can't, not precisely, not ever, no matter how good the instrument. This isn't a failure of measurement. It's not that our equipment is too crude to pin the electron down. It is, as far as anyone has ever been able to determine, simply how the electron exists, genuinely without a fixed position, until something interacts with it closely enough to force the question, at which point it resolves into a location, briefly, and then dissolves back into probability the instant you stop looking. The solidity of your hand, in other words, isn't built from tiny hard spheres stacked neatly together. It's built from clouds of likelihood, repelling other clouds of likelihood, and the repulsion is entirely real, even though almost nothing involved in it has a fixed place to be. So when your fist meets a table, and it feels like something hitting something, that's not matter touching matter. That's forces arguing. Stretch that logic out to the room you're in. The walls, the floor, the mattress underneath you, constructed almost entirely from space, held into a shape by forces too small to see, too fast to feel, too consistent to notice. You've spent your whole life resting your full weight on something that is, by volume, more empty than not. If you added up only the actual mass in your body, every proton, every neutron, ignoring for a moment all that surrounding emptiness, and compressed it down until the gaps disappeared entirely, until nucleus sat directly against nucleus with none of the usual space between, you would not fill a room, or a chair, or even a fist. You would fit into something you could not see without a microscope. A being made of nothing but your own actual matter, with all the empty space finally squeezed out of it, would be smaller than a single grain of sand and would still contain, unchanged, every proton and neutron you've ever carried around inside a body that felt, your entire life, like it took up considerably more room than that. It should feel less solid than it does. It doesn't. That's the strange part. Knowing the arithmetic changes nothing about how the fist feels when it closes. Go one layer deeper than the atom and the emptiness doesn't resolve into something solid either. It just changes shape. The nucleus at the center of that stadium-sized atom is itself made of protons and neutrons, and each of those is made in turn of three smaller particles called quarks, bound together by a force so strong that no quark has ever been observed alone, isolated, sitting by itself the way an electron sometimes can be. And yet, if you ask how much of a proton's mass actually comes from the quarks themselves, the honest answer undercuts the whole idea of solid building blocks going all the way down. The three quarks inside a proton account for only about 1% of its total mass. The rest, the overwhelming majority of the mass that makes a proton, and by extension makes your body weigh what it weighs, comes from the energy of the force holding the quarks together. A swirling, dynamic, binding energy, converted into mass by the same relationship Einstein wrote down for entirely different reasons. Your weight, in other words, is mostly not stuff at all, even at the deepest layer physics has been able to examine. It's mostly the energy of quarks being forcefully, restlessly bound to each other, converted through nothing more mysterious than an equation into something a bathroom scale can register. There's a related strangeness that shows up whenever a particle needs to get from one place to another without technically having the energy to cross whatever's in between, and it has a name that undersells how odd it actually is. Quantum tunneling. Classically, an object without enough energy to climb over a barrier simply doesn't get over it. A ball rolled toward a hill it can't climb, rolls back down every single time, no exceptions. A particle, though, doesn't obey that rule with total certainty, because its position is never perfectly fixed, only probable. There's always some small, calculable chance that a particle will simply appear on the far side of a barrier it shouldn't have had the energy to cross, without ever actually being detected in the space in between. Not squeezing through a crack, not finding a shortcut, but resolving into existence beyond the barrier in a way that has no equivalent in the world your hands understand as solid. This isn't a rare theoretical curiosity kept alive only in physics classrooms. It's the reason the sun burns as steadily as it does. The protons fusing together at the sun's core, the very ones responsible for the neutrino from an earlier chapter, don't actually have enough thermal energy on average to overcome their mutual electric repulsion and fuse at the rate the sun requires. They fuse anyway, constantly, because a small fraction of them tunnel through the barrier rather than climbing over it, borrowing a probability instead of the energy a classical calculation says they need. The sun's entire dependable output, the warmth eventually reaching your face on any ordinary afternoon, rests partly on particles quietly refusing to be stopped by a barrier that, by every rule your body operates under, should have stopped them completely. There's a reason it doesn't collapse under its own arithmetic, and the reason has a name most people never learn outside a classroom. The Pauli exclusion principle. The same Pauli who spent a previous chapter worrying about missing energy in beta decay. It states, in its plainest form, that no two electrons in the same atom can occupy the exact same quantum state at the same time. A rule with no equivalent in the world your hands actually feel, where two things can, in principle, sit in the same place if you push hard enough. Electrons refuse this categorically. It's this refusal, more than the electromagnetic repulsion usually credited for it, that keeps matter from simply passing through itself, keeps a chair from collapsing into the floor it's resting on, keeps the atoms in your own body from folding down into that grain of sand density the moment gravity gets the chance. Every time you sit in a chair without falling through it, you are, in a very real sense, being held up by billions of electrons refusing, on principle, to be anywhere another electron already is. There's a version of this same emptiness that shows up not in the space between electrons and a nucleus, but in the very particles doing the orbiting, and it took physics much longer to accept than the emptiness of the atom itself, because it asks you to give up the idea that a thing needs a fixed size and shape to count as real. As far as any experiment has ever managed to determine, an electron has no measurable size at all, not extremely small, not smaller than anything else, but genuinely, mathematically point-like, a particle with mass and charge and no volume whatsoever to speak of. Physicists have tried for the better part of a century to find some structure inside it, some minimum radius where the electron's stuff actually starts and stops, the way you'd expect any object to have edges eventually. Every experiment sensitive enough to test the question has come back the same way. No edge found consistent with a literal point. It's a strange thing to build a fist out of, a hand made of atoms, and atoms made mostly of empty space, and the small non-empty part of each atom populated partly by particles that, as far as anyone can tell, take up no space at all, only a location, briefly, when something forces the question. Slow the whole picture down further, because there's a middle layer to this that's easy to walk past. Between the point-like electron and the true emptiness surrounding the nucleus, there's a kind of restless activity that never fully goes still, not even in a perfect vacuum, not even in the coldest, quietest laboratory that has ever been built. Quantum field theory, the framework underneath all of this, describes what looks like empty space as actually being full of fields in their lowest possible energy state. Not nothing exactly, but as close to nothing as the universe is willing to allow, and even that lowest state isn't perfectly still. Pairs of particles and their opposite charged twins are allowed, briefly, to appear out of this restless field and vanish again almost immediately, borrowing the energy needed to exist for a span of time too short to ever measure directly, then paying it back by annihilating each other before anyone could catch them in the act. This isn't a metaphor invented to make an equation sound more dramatic. It has a measurable consequence called the Casimir effect, first predicted in 1948 and confirmed experimentally decades later. Place two uncharged metal plates extremely close together in a vacuum, closer than a human hair is wide, and they will draw toward each other, pulled by a tiny but real force, because the narrow gap between them restricts which of these fleeting particle pairs are allowed to form there compared to the open, unrestricted space on the outside of the plates. The plates aren't being pushed together by anything you could photograph. They're responding to the difference in how much nothing is allowed to happen in one place compared to another, which is among the strangest sentences physics has ever required anyone to say out loud, and also, by now, one of its best confirmed. Which brings the fist back into view, differently than before. What closes when you close your hand is not simply matter meeting less matter than expected. It's a boundary made of forces refusing to overlap, built from particles with no measurable size, surrounded by a version of empty space that was never actually still to begin with, humming quietly with activity too brief and too faint for any nervous system to register. None of this changes how the fist feels. That's still the strangest part every time it's said again. The arithmetic underneath your body has always been this unfamiliar, and your hand has never once needed you to know that in order to close. The room is quiet. The fist is closed. Almost none of it, anywhere, all the way down, is actually there in the way you assumed. What the scale keeps refusing to say. For most of the last century, astronomers thought they had counted everything worth counting. Stars, obviously. Galaxies, obviously. Gas clouds, dust lanes. The faint smear of light from thing too far to resolve into anything but a smudge on a photographic plate. Add it all up, weigh it by how much light it gives off, and you get a number, a total mass for the visible universe, or at least the observable slice of it that our instruments could reach. Then you compare that number to how the universe actually behaves, not how it should behave, mathematically, if the visible mass were all there was, how it actually moves, expands, clusters, bends light around its densest points. The two numbers don't match. Stop. They don't match by a small margin, not a rounding error, not something you could blame on an old telescope or an undercounted galaxy cluster, somewhere out past the range of easy measurement. They don't match by most of it. Something like 95% of the total mass and energy content of the universe isn't accounted for by anything we can directly see, weigh, or photograph. I've read that number 100 times and it still doesn't sit easily. 95%. As if you'd been keeping a household budget your whole life, confident in every entry, only to discover the actual bank statement bears almost no resemblance to your ledger. Not because you cheated, but because you were never shown most of the transactions. Roughly a quarter of it is the dark matter already mentioned, the scaffolding, the halo, the thing that holds galaxies together without shining. The rest, the much larger rest, is something else entirely, something with a name so plain it almost sounds like a placeholder, because honestly, it is one dark energy. Not matter at all. Something pushing space apart, accelerating the expansion of the universe, discovered only because distant supernova kept turning up fainter, meaning farther, than an unaccelerated universe would allow. The discovery itself came from two competing teams of astronomers who spent the 1990s racing each other toward what everyone involved assumed would be the same, unremarkable answer. Both groups were studying a particular kind of exploding star, called a Type 1 supernova, chosen because these explosions reach almost exactly the same peak brightness every time, regardless of which galaxy they happen in. A reliable enough standard candle that, comparing how bright one appears against how bright it should appear, given its distance, lets you measure how the universe's expansion has changed over time. Everyone expected to find that the expansion was slowing down, dragged backward by the gravity of all that mass, visible and dark alike. pulling against the outward rush left over from the Big Bang. Slowing down was the sensible answer. Slowing down was what every model had predicted for decades. Both teams, working independently, checking each other's methods with open suspicion, because a result this important couldn't be trusted from only one source, found instead that the most distant supernova were fainter than a slowing universe could explain, meaning they were farther away than expected, meaning the expansion hadn't been decelerating at all. It had been speeding up. Neither team believed their own numbers at first. They checked for dust that might be dimming the light artificially, checked for errors in calibration, checked for anything that could explain the result away as a mistake rather than a discovery, and found nothing that resolved it. The acceleration was real. In 2011, the leaders of both teams shared the Nobel Prize for a result that neither had set out to find, and that, for a while, neither had wanted to be true. Nobody claims to know what it actually is. Say that plainly, because it deserves to be said plainly. The majority of everything that exists is currently, as far as anyone can prove, a placeholder in an equation that happens to make the numbers balance. The most common way physicists describe dark energy is as a property of space itself rather than a substance moving through it, something built into the vacuum so that every cubic meter of truly empty space carries a small, fixed amount of this outward push. And as the universe expands and creates more space, it creates more of the push along with it, which is part of why the acceleration itself keeps accelerating rather than leveling off. This idea traces back, strangely, to a term Einstein added to his own equations decades before any of this was observed, a cosmological constant, inserted not because the data demanded it, but because Einstein, in 1917, wanted his equations to describe a static, unchanging universe, the only kind anyone assumed existed at the time, and his equations, left alone, insisted on either expanding or collapsing. He added the constant as a kind of counterweight, a fudge factor to hold the universe still by hand. When Edwin Hubble's observations in the following decade showed the universe was expanding after all, Einstein reportedly called the cosmological constant his greatest blunder and dropped it from his work entirely. 7 decades later, the supernova surveys handed it back to him, except now it wasn't holding the universe still. It was the very thing pushing the expansion to accelerate, doing almost exactly the opposite job Einstein had originally built it for, resurrected from a mistake into what may be the dominant force in the entire universe. Say that plainly, because it deserves to be said plainly a second time. A term Einstein inserted for the wrong reason, then abandoned as an embarrassment, turned out, as far as the data can currently tell, to describe most of everything that exists. There's no settled account of what dark energy is made of, if made of is even the right way to phrase a question about something that might not be a substance at all. One line of thinking treats it as the intrinsic energy of empty space, calculable in principle from quantum field theory, except when physicists actually run that calculation, using their best understanding of how particle fields behave even in a total vacuum. The predicted value comes out roughly 120 orders of magnitude too large, a mismatch so enormous it's sometimes called the worst prediction in the history of physics, precise language for an embarrassment nobody has resolved. Another line of thinking treats dark energy not as constant at all, but as something that might change over cosmic time, a dynamic field rather than a fixed property, though the evidence for that possibility remains thin and contested. What's left, underneath both approaches, is an honest admission rare enough in a field this confident about most other things. The majority of the universe's contents are currently described by a placeholder, doing its job in the equations perfectly, while nobody involved can yet say what it actually is. Follow the acceleration far enough forward, and it starts to describe not just how the universe has behaved, but what it's likely to become, and the possibilities on offer aren't especially comforting, though none of them will arrive on any timescale that touches you personally. If dark energy really is a fixed, unchanging property of space, the most widely favoured outcome is something cosmologists have taken to calling the heat death, or sometimes the big freeze, an unimaginably long, slow spreading out, in which galaxies not already gravitationally bound to each other drift farther and farther apart, faster and faster, until eventually every galaxy outside our own immediate cluster recedes past the point where its light could ever reach us again, vanishing, not by moving away in any dramatic sense, but simply by the space between here and there expanding faster than light can cross it. Trillions of years after that, the last stars burn out, one by one, and are never replaced, because star formation requires gas clouds dense enough to collapse under their own gravity, and the raw material for that runs out long before the universe does. What's left eventually is a cold, dark, almost featureless expanse, thinning forever, approaching but never quite reaching a true and final stillness. If, instead, dark energy turns out to be a dynamic quantity that strengthens over time rather than staying fixed, a more violent ending becomes possible, the so-called Big Rip, in which the outward push eventually grows strong enough to overcome not just the gravity holding galaxies together, but the forces holding galaxies, then stars, then planets, then atoms themselves intact, tearing the universe apart from the larger scales down to the smallest in a finite and calculable amount of time rather than an infinite fade. Current measurements lean toward the quieter ending, the heat death rather than the rip, though the honest answer is that the measurements aren't yet precise enough to rule either one out completely, which means the ultimate fate of everything currently hinges on a number. Scientists are still working to pin down to a decent number of decimal places. None of this is close. The earliest estimates for either ending cite tens of billions to trillions of years out, a span of time next to which the entire history of life on Earth is a rounding error too small to register. It's mentioned here not as a warning, but as a kind of scale check, a reminder that the same mysterious pressure responsible for tonight's quiet expansion of the universe is also, patiently, writing the last chapter of it, on a clock so long that writing feels like the wrong word entirely, too quick a verb for something unfolding this slowly. Roughly a quarter of it is the dark matter already mentioned, the scaffolding, the halo, the thing that holds galaxies together without shining. The rest, the much larger rest, is dark energy, pushing outward, patient, unnamed in any deeper sense than the placeholder it started as. They pull with no hands. Right now, something is happening between you and the chair, or the bed, or whatever is holding you up. A quiet, mutual insistence that you stay close to it, and it stay close to you. It has a name: gravity. Say it once, and let the word go. because the word was never going to do the job of explaining what's actually occurring, which is stranger than a word this ordinary should be allowed to describe. Nothing is reaching toward you. There's no rope, no field you could photograph, no hand extending from the Earth's core up through the floor into the small of your back, and yet you are held continuously by something with no visible mechanism, exerting a pull that has never once, in the history of measurement, been caught arriving. For most of human history, this was simply accepted as the nature of things. The way falling was just what objects did, requiring no more explanation than water being wet. Isaac Newton was the first to write down a version of the pull precise enough to predict, not just describe, a single equation connecting the fall of an apple to the orbit of the moon, the same force at every scale, obeying the same inverse square relationship, regardless of whether it was holding a person to a chair or holding a planet in its yearly circuit around the sun. It was, by any measure, one of the great unifications as the history of thought, one law, one force, governing a dropped stone and the entire visible architecture of the solar system. Newton himself, by his own account, found the underlying cause deeply unsatisfying, even as he perfected the mathematics describing its effects. He admitted in his private letters that the idea of one body acting on another across empty space, with no medium and no contact of any kind, felt to him like an absurdity that no philosopher competent in these matters could ever accept, and then spent the rest of his career declining to speculate further, famously writing that he framed no hypotheses about what gravity actually was, only how it behaved. The mathematics worked. The mechanism stayed a mystery for over 200 years, quietly holding up bridges and predicting eclipses the entire time, indifferent to the fact that nobody could say what it actually was. Zoom out. Same pull, same invisible insistence, holding the moon in its slow circle, dragging the ocean sideways twice a day, bending the paths of comets that haven't been near enough to see in centuries and won't be again for centuries more. Zoom out further. The pull holds galaxies to each other across distances so vast that light, the fastest thing there is, takes millions of years just to cross the gap, and still they know where each other is. Still they respond. Einstein reframed the whole thing a century ago, suggesting it isn't a pull at all but a shape, mass bending the space around it, the way a heavy ball bends a stretched sheet, and everything nearby simply rolls along the curve without needing to be pulled anywhere. That explanation works better than the old one. It predicts things the old one couldn't. It still doesn't make the sensation of sitting in a chair feel any less like something invisible has its hand on your shoulder. Stay with the shape a moment longer, because the stretched sheet is a helpful picture, and also, in one important way, a misleading one. The rubber sheet analogy always shows mass bending a flat surface downward, which quietly assumes the very gravity it's trying to explain. Something has to pull the ball down into the sheet to make the dent in the first place. What Einstein actually proposed goes a step stranger. It isn't a two-dimensional sheet warping downward under weight. It's the full four-dimensional fabric of space and time itself, curving in every direction around any mass, with no downward required and no outside force doing the pulling. An object moving through that curved space isn't being pulled off a straight path at all. It's still going as straight as it possibly can, following what's called a geodesic. the natural, unforced path through space that's been warped by the mass nearby. The way a straight line drawn on a globe still looks straight to whoever's drawing it, even though from farther away, in 3 dimensions, it clearly curves around the sphere. The Earth doesn't fall toward the Sun because the Sun reaches out and grabs it. The Earth is moving in the straightest possible line available to it through a region of space and time that the Sun has bent, and the bent path happens to loop back on itself once a year. There's a strange consequence hiding inside that reframing that has nothing to do with falling and everything to do with time itself. And it's worth sitting with because it's been tested and confirmed with instruments precise enough to leave no real room for doubt. If mass curves space and time are, in Einstein's framework, really one interwoven fabric rather than 2 separate things, then mass has to curve time as well, which means a clock closer to a large mass runs measurably slower than an identical clock farther away. This isn't a thought experiment. Atomic clocks placed at different altitudes on Earth, one at sea level, one at the top of a mountain, or one in a satellite orbiting far overhead, actually disagree with each other by amounts small enough to require extraordinary precision to notice, but large enough to matter in practice. GPS satellites carry clocks that run measurably faster than clocks on the ground, simply because they sit farther from the Earth's mass, in a region where gravity's grip on time is a little looser, and if that difference weren't corrected for deliberately, hour by hour, the location data your phone relies on would drift by several miles a day, becoming useless within hours. Gravity, in other words, doesn't just hold you to the chair, it's quietly, constantly, adjusting how fast time passes for you compared to someone standing somewhere else, someone closer to or farther from the same mass at every moment, whether either of you ever notices or not. If mass can curve the fabric of space and time, then a sudden, violent movement of mass should send ripples through that fabric outward in every direction, the way dropping a stone into still water sends ripples across the surface. And Einstein predicted exactly this in 1916, calling them gravitational waves, then spent much of the rest of his life doubting whether they'd ever actually be detectable, since the ripple produced by even a catastrophic cosmic event would arrive, at Earth stretched and compressed by an almost unimaginably small amount, a distortion smaller than the width of a proton spread across a detector miles long. It took a full century of patient engineering to prove him right. In September of 2015, twin detectors in Louisiana and Washington state, each an L-shaped instrument with arms 2.5 miles long, built to measure exactly this kind of impossibly small stretching, using lasers bounced back and forth with extraordinary precision, caught a signal lasting a fraction of a second, a rising chirp when converted to sound climbing rapidly in pitch before cutting off abruptly. It was the signature of 2 black holes, each dozens of times the mass of the Sun, spiraling into each other and merging over 1 billion years ago, in a collision so violent it briefly outshone, in gravitational wave energy alone, every star in the observable universe combined, and the ripple from that event travelled outward for well over 1 billion years, crossing an expanding universe the entire way, arriving at 2 instruments on Earth built specifically and only to notice it. It was the first time anyone had ever directly detected gravity in motion, rather than inferring its presence from something else, and it opened, essentially overnight, an entirely new way of observing the universe, not through light of any kind, but through the trembling of space and time itself. There's a place where all of this careful, confirmed, century-old understanding simply stops working, and it's worth naming honestly rather than smoothing over, because it's one of the genuine open wounds in physics. Gravity, as Einstein described it, is a theory of smooth, continuous curves, space bending gracefully, predictably, at every scale from a falling apple to a merging pair of black holes. Quantum mechanics, which governs everything at the scale of atoms and particles, describes a world that is anything but smooth, probabilistic, discrete, built from sudden jumps rather than continuous curves, a formalism that has been tested to extraordinary precision and has never once failed at the scales where it applies. The trouble is that these two enormously successful descriptions of reality have never been reconciled into one another. Try to describe gravity using the same quantum rules that govern every other force, and the mathematics breaks down, producing nonsense results. Infinities where there should be finite numbers, especially at the extreme densities found at the center of a black hole or in the first instant of the universe's existence, exactly the places where you'd most want a working theory of quantum gravity to actually apply. Decades of effort, string theory, loop quantum gravity, and a handful of other frameworks, each with committed defenders and each still unconfirmed by any experiment, have tried to close that gap, and none has yet succeeded to the field's general satisfaction. It means that, at its foundation, the pull holding you in your chair right now is described by a theory that physicists know, with total confidence, cannot be the final answer, because it refuses to speak the same language as the other three forces of nature, all of which learned to speak that shared quantum language decades ago. Nothing is touching you. Something is, unmistakably, touching you. 5% and everything after. So here's the number, finally, plainly, the one that's been sitting underneath every chapter so far without anyone saying it outright. The stuff you can touch, weigh, photograph, build a civilization out of: stars, skin, steel, oceans, the chair, the neutrinos that passed through it, the very fist that closed around nothing and called it solid. All of it together, every atom in every galaxy ever observed, accounts for something like 5% of everything that exists. 5%. Sit with that a moment before the rest of the sentence arrives, because the rest of the sentence tends to rush past it. About 27% is the dark matter, the scaffolding holding galaxies together with no light of its own, detected only by what it does to everything nearby, never once by what it is. And the remaining 68%, the vast, overwhelming majority of the universe, is dark energy. The thing pushing space itself apart, accelerating an expansion that was supposed to be slowing down, and instead just kept going faster, discovered by astronomers who were looking for the brakes and found the accelerator instead. None of this was ever absent. That's the part that took me the longest to actually feel, rather than just know. It was there the whole time, in the spinning galaxy that wouldn't fly apart on its own. In the pull with no hands, holding you to a chair that was never designed to explain itself. In the pairs of particles flickering into being and cancelling out in the coldest, emptiest patch of space you could point a telescope at, doing work nobody asked them to do. Go back if you want through every room this series has walked you through. The neutrinos, the gravity with no mechanism, the gap inside the fist, the window of light your eyes were built for and nothing past it. Each one felt at the time like its own separate strangeness, a single unaccountable thing sitting alone in its own chapter. They weren't separate. They were the same 5% or the other 95 showing up in different rooms of the same house. It's worth walking back through the house once more, slower this time, because the connections between these rooms are easy to miss on a first pass through, and they're the actual point, more than any single fact was. The neutrinos streaming through your chest and the dark matter holding your galaxy together are, in a strange way, cousins. Both belong to a category physicists sometimes call weakly interacting matter, particles or near particles that barely notice the ordinary world around them, that pass through walls and planets and each other with something close to indifference. The difference between them is almost entirely a matter of degree. Neutrinos interact just often enough, just rarely enough, to occasionally be caught in a tank of water under a mountain after decades of patient waiting. Dark matter, as far as anyone has managed to determine, interacts even less than that. Perhaps not at all, beyond the pull of its own gravity, which is the one thing about it that has never once failed to show up in a measurement. Two members of the same broad family, one barely visible to the most sensitive instruments ever built, the other invisible to every instrument that has ever tried. The gap inside your fist and the gap between galaxies turn out to be the same gap too, just at wildly different scales, and once you notice that once, it's hard to stop noticing it everywhere else. An atom is mostly empty space held together by fields too faint to see. A galaxy is mostly empty space, threaded by an invisible halo, held together by the same gravity that was never explained beyond the fact that it works. The visible universe, the stars, the skin, the steel, sits inside both of these emptinesses like a small bright decoration inside a much larger, quieter structure at every scale anyone has ever managed to examine, from the space inside a single hydrogen atom to the space between one galaxy and the next. And gravity, the pull with no hands from a few chapters back, turns out to be the thread running through literally all of it, the same force curving space around the nucleus of an atom in some faint, negligible way, curving it around your own body just enough to hold you in a chair, curving it around a galaxy enough to bend the path of light from something far behind it, curving it at the largest scale anyone can measure, around the whole visible universe in a way that dark energy is now slowly and irreversibly working against. Every mystery raised in this series eventually leads back to the same handful of unresolved questions asked at different distances. What is actually pulling? What is actually there when nothing visible is? And why does the universe seem built almost entirely out of things that refuse to be seen directly, saving the 5% you can touch for last, almost as an afterthought? You were never looking at the whole house. You were looking at the part with the lights on, and somewhere past the edge of every lit room in this house, past every wall you've ever leaned against without noticing it was mostly space. The rest of it is still there, still doing whatever it does, without needing you to notice, without needing you to understand it, without needing anything from you at all. There's a comment from a much earlier upload than this one that stayed with me longer than most. Someone writing in late, the way most of you seem to write in, saying that learning all of this made them feel smaller in a way they hadn't expected to mind, and then, a few lines later, admitting they weren't sure smaller was even the right word for it. I've turned that over more than once since. I don't think it makes you smaller exactly, to learn that most of what holds you up and most of what fills the space around you is invisible, unnamed, unresolved even to the people who've spent entire careers trying to pin it down. I think it makes the visible 5% slightly more remarkable than it looked before you knew what it was floating in. A thin, bright, improbable layer of stars and skin and steel, sitting on top of a much larger structure that asks nothing of it and gives it, in return, exactly enough gravity to stay in one piece. It hasn't changed since the last chapter. It's just further from the light than the rest of it. A few percent of everything, quietly outnumbered, going on breathing along with you in the dark,